Hello everybody, welcome to your video over 2's complement in binary systems. If you have no idea what that is and you just accidentally ran into this video, or you need to learn about it for something, or if you know what it is and you want to learn more about it, well, 2's complement is a method used to store negative values in binary. So if you know anything about how binary works, basically you have zeros and ones. 0 is 0, and then we have 1, which is 1, and then to represent 2, we have to go to the next place value and put 1, 0, and we can keep doing that, adding more place values and so forth. But how do we represent a negative value? Because if you noticed, the numbers only got bigger. Well, this is something known as a sign bit. So when we're working with binary, let's say we have the number 101. Every single one of these placeholders is known as a bit. So a bit is just 1 or 0. That's what a bit is. When we have 8 bits, we would say we have a byte and so forth. So if you know about bytes, a byte consists of 8 bits. So a bit is just a 1 or a 0. A sign bit is used to represent a negative value in binary. So let's say we have a 3-bit word length. That means we have 3 bits in the number system, and we're going to represent every single possible value we can make with 3 bits. If you watch my introduction to binary video, this may look familiar to you. So we had 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, oops, my bad, that's not a 0, that's a 1. Come on, Caleb, get it together. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So here's how you represent 0, 1, 2, 3, 4, 5, 6, 7. So as you can see, the highest number we have, highest value, is 7, 1, 1, 1. And we have a total of 8 values, 1, 2, 3, 4, 5, 6, 7, 8. The reason it's not 7, well, we have to include the 0, so this is 7, not 8, with 8 total values. Well, so we have a range from 0 to 7. Well, how can we represent negative values? Well, we could use a sign bit, and let's say we could say the first bit farthest left, the first left bit, we could use this as a sign bit to represent whether the number is positive or negative. So we could say 0 is positive and 1 is negative. So now you can see we can represent positive numbers and negative numbers. There's only one problem here. For example, this is 0, this is 1, 2, 3. This is negative 0, which is another problem. We'll get into that in a second. Negative 1, negative 2, negative 3. So now all we can represent is negative 3 all the way to positive 3. So the same amount of values, besides the double 0 thing, so one less value actually. And the highest number is 3, the lowest number is negative 3. So basically we just move the range to cover some negative numbers. Well, the other problem with this system is, well, you could see we have 2 zeros, positive 0 and negative 0. That means we have 2 values that pretty much mean the same thing, so the total range of values is 1 less. Because if we have 0 in there twice, we get negative 3, negative 2, negative 1, 0, 1, 2, and 3. How many values is this? 1, 2, 3, 4, 5, 6, 7. So now we only have 7 possible values because 0 is in there twice. Well, 2's complement is a strategy to fix this problem. It still has a sign bit, so you need to know about sign bits. And if the first digit to the left, the farthest left digit, I should say, if it's a 0, it's positive. If it's a 1, it's negative. So this is a negative number. That is a positive number. So how does this work? Well, every single number in binary has a 2's complement equivalent. So let's say we have the number 1, right? And it's a positive 1. that means we have 0, 1. Okay? Now, we can basically store these within a bit word. Let's say the bit word length is 8 bits. That means we have to take up 8 spots. 8. So now we can represent this as 0, 0, 0, 0, 0, 0, 0, 1. Now, if you remember before, we had 0, 1, and we said this was the sign bit. That's because it's the farthest left 0. So it doesn't mean this one, it means this one. So I put it in an 8-bit to represent that it's not this one, but this one. Now, we can convert this to what's known as 2's complement. And to do this, here's what we do. We invert every single bit within this bit word. So now we get 0, 1, 1, 1, 1, 1, 1, 1. And then, that's the first step. So the first step is to invert every single digit. All the zeros become 1s. We just drag it down, 1, 1, 1. But 1s become zeros. And then the next step is to add 1. So this 0, if we add 1, this is now going to become, 1. So this number right here, this is a representation for -1. So that is -1. So, to convert back, what we can do, let's say we have -1 now. 1, 1, 2, 4, 5, 6, 7, 8. This is -1. What we can do is convert them all to zeros. Or, basically switch it. So if this was a 0, for example, it would become a 1. But in this case, they're all 1s. So all we have to do is make them all zeros. 4, 5, 6, 7, 8. And then what we do, just like in the way to convert to 2's complement, to make it positive, we also add 1. This is +1 from -1. So it makes more sense. Now, why do we use this system? Well, the very first thing is we only have 1 0. So, for example, this is 0. We can't convert this to binary, because if we converted it to binary, we would get 1 1 1 1 1. We would get 1 2 3 4 5 6 7 8 1s, and then we add 1. So we would basically push all these over, and then we would get 1 0 0 0 0 0 0 0 0. Well, we're stuck in 8-bit word lengths. This means this 9th bit we just added is the overflow system gets rid of it. So now it just cuts it off, and we're stuck with 0 0 0 0 0 0 0 0. That is still the same thing as this. So the 2's complement for 0, the -0, it doesn't work. So we have an extra value we can use within an 8-bit system. The other thing we can do is we can work, instead of subtracting binary, we can always use addition. So I just created a video over addition and subtraction of binary numbers. Well, we can use the addition system with 2's complement to do a few things. We can subtract as well as add. So we actually use addition to subtract. It's kind of weird, but I'll get into it. We can also subtract numbers that are smaller. So like, let's say we have this number here, positive number. And then we have another positive number right there. Or I guess you could say this number is bigger than this number. So we can use subtraction for that. But what if we flip these and put this one on top and this one on bottom, and we wanted to subtract them? Well, we're going to get a negative number, which we can't do that with normal binary subtraction without getting super complicated and adding a sign bit in, having to worry about double zeros and so forth. So we have 2's complement, which we can use to subtract larger numbers from smaller numbers. When we're working with this 2's complement system, let's say we are in a 4-bit word system and we want to represent 2. Well, that 2 is represented like this in binary, because this is the 2's place. Well, if we're in a 4-bit word system, it would be like this. This represents positive 2. So this first bit on the left, so not the first bit, but the first bit on the left. So the farthest left bit is the sign bit, which tells whether it's positive or negative. Hopefully you got that by now. So we could also have, which by the way is not -2, because we did not do the processing, but this is a negative number. So let's figure out how we could represent -2. Well, first, we change all the digits, so 1, 1, 0, 1. We invert them, and then what we do is we add 1. So 1, 1, 0, 1 plus 0, 0, 0, 1. To do this, well, we add these, and we get 1, 0, 1, 1, 1. Or you can just think of, rather than 1, we could have 2, but it doesn't really matter. So here is a representation of -2. So now we can also use this system to represent mathematics. So let's try 2 plus -2. So we have 0, 0, 1, 0. This is 2. And then we convert that. I forget what I had, so we had 1, 1, 0, 1. So we had 1, 1, 1, 0. This is -2. So we basically have positive 2 plus -2. So how does that work? Well, if you know much about math, adding a negative is basically the same thing as subtraction. That looks bad. Basically, this, you can think of this as adding, for example, let's say I have $500, okay? I have $500, or whatever currency you're using in your country, in my bank, okay? And then I get a bill for $500. I add in a bill of $500. So now, what is a bill? A bill in general is designed to subtract money. So if you think about it, I'm adding and taking away money. I'm adding the bill in, which takes away $500. So it's sort of like adding -$500, which in reality is like subtraction. So with the 2's complement system, we can use subtraction by adding a negative number, and we can use addition as well. So that is why the 2's complement system is good. We don't have to worry about subtraction. We can use all addition. So, well, what is 2 plus -2, or 2 minus 2? Well, the answer is going to be 0. So we can try to work this out and figure out what we're going to get. So we can just ignore this over here. We add these together. 0 plus 0 is 0. 1 plus 1, we have to carry the 1, drop a 0. 1 plus 1, carry the 1, drop a 0. 1 plus 1, carry the 1, drop a 0. So this is the 1's place, 2's place, 4's place, 8's place, 16's place. So the answer is 16. That's not right. What's up with that? Well, if you look, we are in a 4-bit word system. This limit allows this to work. So basically, we can only have 1, 2, 3, 4 bits. Anything after that is ignored. So now, our answer is 0, which is the correct answer. Let's try something such as 4 minus 6. Well, the actual result is going to be -2. This is because we subtract 6 from 4. So to represent, be able to For us to do this in 2's complement, we're going to make this 4 plus negative 6. Pretty much the same thing. I talked about this earlier. So let's do this. First, let's figure out the binary value of 4. So we have the 1's place, 2's place, 4's place. So 1, 0, 0. Here is the binary value of 4. We also have a sign bit, so we're in a 4-bit system. We're going to figure out the 2's complement of 6. In order for us to do this, we first find 6, 1, 1, 0. Right? So here is 6. This is because this is the 4's place and the second 2's place. 4 plus 2 equals 6. Now we convert this, so 1, 0, 0, 1. Basically flip all of the bits to the opposite, and then we add 1. So we get 1, 0, 1, 0. So here is the 2's complement of negative 6. Shoot, what was it again? I don't know. So let me do it real quick again. 0, 1, 1, 0, 1, 1. Alright, 1, 0, 1, 0. So this right here is basically saying 4 plus negative 6. Then we add it. 0, 1, 1, 1. Alright, so now we have a 2's complement, negative representation of a value. So now we have to figure out what this value represents. So we convert it the other way around. So we flip all of these, we get 0, 0, 0, 1, and we add 1. 0, 0, 1, 0 is the final result. This right here, this is the equivalent of 2. That means this right here is the 2's complement representation of negative 2. Pretty complex system, but it works, and we can do more complex mathematics with the 2 complement system. So this is a binary representation of negative 2. We can try another one if you would like. Let's try to figure out 8 minus 16. So what place value is 16? 1, 2, 4, 8, 16. So we have 5 bits plus a sign bit. So we need a total of 6 bits. So we are in 6-bit word. 6-bit word length. Alright, so this is what's required. First, let's figure out what 8 is. 1, 2, 4, 8. Here is 8. Now, let's figure out what 16 is. So we're going to subtract 16 from 8. Another way to represent this is 8 plus negative 16. So let's figure out the negative value of 16. So let's first figure out 16, which would be 1, 0, 0, 0, 0. That's because this is the 16th place. And then we convert this. So 16, we convert it to 2's complement with the negative sign. So we just flip all of these bits, and then we add 1. So the final result is going to be 1, 1, 0, 0, 0, 0. Okay? So this is negative 16. 1, 1, 0, 0, 0, 0. We're going to add these. These become 0, these become 0, these become 0. This becomes 1, this becomes 1, and this becomes 1. So this is the value we have. Now this is a representation of a negative value, so we have to figure out what negative value it's representing. That means we have to convert it to a positive number by reversing the 2's complement system. So we get 0, 1, not 1, sorry. 0, 0, 0, 1, 1, 1. Now, we add 1, so this becomes 1, 0, 0, 0. What is this value? Well, 1, 2, 4, 8. So it's in the 8th place, so that means the final value we got was 8. And if you remember what we started with 8 minus 16. So the final value is -8, which is correct. So that is the example of 2's complement. So in quick review, 2's complement is a system we can use to represent binary values. The good thing about it is there's no double zeros, so the only zero value is 0, 0, 0, and however many bits you have. This is because these 2's complement representation for -0 would become 1, 1, 1, 1 plus 1, which would give us 1, 0, 0, 0. This is in the overflow bit because we're obviously in a 4-bit system. We have 1, 2, 3, 4, so it's going to go back to 0, 0, 0, 0. Pretty awesome, I know. So the way we convert a positive number to a negative number, so if we have 1, 0, 1, this is equal to 4, 5, and it's positive. So we're in a 4-bit system, we convert it like this. 1, 0, 1, 0. We flip all the bits, so if it's 0, it becomes 1. If it's 1, it becomes 0. And then we add 1. So this up here is 5. This down here is -5. And then we can also convert it back by doing the same process. 0, 1, 0, 0, adding 1, 1. And this becomes 5 again. Alright, so then we can use this to do mathematics. We can always use addition because we can subtract by having a positive. We can have a number over here, and we can add a negative number. So this is going to come out as 0. You can also use 2's complement to do things such as 18 minus 24, which is going to come out as -6. The only thing is, you're going to have to convert the -6 2's complement value into non-2's complement value to figure out what value it represents. So it will come out, once you convert it, will come out as positive. That is because we are figuring out what number it represents in 2-bit in the 2's complement system. So let's say we have a value, just ignore this, let's say we have a value 111010. This is a negative number. We automatically know it's a negative number. But what negative number is it? We have to convert it to a positive number to figure out. So we flip all the signs, and then we add 1. So we get 0, 1, 1, 0, which this is equal to 6. So this is -6 right here. It's -6. It is -6. -6. -6. So that's pretty much a quick review of everything for 2's complement. Hopefully that was helpful. If it wasn't, be sure to comment and tell me what I can improve upon or whatever else. So thank you. Be sure to subscribe and like this video. I will see you in the next video.